Okay, so, so I'm going to talk to you about something that is extremely new in the sense that really the results I'm showing today are something that have been produced in the last weeks, and actually some last night when I was preparing the talk. And is built upon a story on which I've worked for a long time, that is the story of colloids. And now we use colloids to test and discuss different aspects of classes, right? This has been, I'm a soft matter scientist and I've been working on this domain since the beginning of my PhD basically. So since most of the people here are students, I have nothing to teach because this is a research seminar, but I would like to start my seminar by putting you in contact with some way of thinking that I've learned from somebody and that helped a lot during my research. And this is what I would call the 4 Stanley-Sastry question, because I learned them from Sastry, who reported to have learned such a question from G. Stanley. So I call them the Stanley-Sastry questions. So the idea is, when you think about the problem of research, to split it up in 4 questions. And I mean, it sounds really natural, but it's very easy to lose them when we actually make a project of research. And so the 4 question is, what did we know? So when we started to do our job, when we started to look for something, where did we start from and what was known before? This is justifying us to where we are going next, right? And then of course, what did we do? So what is actually your research? What are the steps that brought you to build your result that you then show and discuss? What did you find? Once you have discussed all this cycle, it's the time to say how your results are framed in terms of what's new. And in this is sort of why should I care about what I'm doing? As a matter of fact, when we do this, a bit of why should I care is a bit at the beginning of the process as well, of course, because I mean we don't start to do something that we don't care at all. But let's say, for the sake, I will organize my talk in these 4 steps, right? So that we know what we're talking about. So what did you know? So I will start about. Apparently, there's not been this much discussion about soft matter in this first week. So I will give you at least the frame of what is my domain of research, what I'm doing, and what are the key words in the domain of colloidal science. And soft matter is a branch of condensed matter where there is a lot of work and is extremely applied field where a lot of our daily life system with which we are very familiar. And so there are different, I mean, one thing that is impossible, I mean, I teach soft matter in 3-4 different courses. It's always extremely tough to explain and what is soft matter. And there are a gazillion ways of doing that. And so most of them are correct, but it's really, really tough. And so I've just picked ones, and just because I want to talk about colloids and I don't have the time to make a full lecture about soft matter. To give you an idea, one of the possible presentations that I do like quite a bit is this idea of putting the different system of soft matter. So soft matter contains a lot of different systems on this triangle here, where you have on one side colloids, on the other amphiphiles, and on the other polymers. So you have heard a lot about polymers and amphiphiles during the Sanat lectures. I'm basically want to focus on this part here that was discussed also in his talks, but maybe a bit less than what was discussed here. And the idea of colloids is that they are solid particles dispersed into something. And the idea on this triangle is that here on this axis you go into elongation, so you start to have rigid rods, then you start to have flexible polymers, less flexible polymers, and then flexible polymers. And on this side here, you start to beat some tendencies of your particle to like and not like water. And then in the extreme case, you have surfactants. And if you want in this range here, which is more or less the range in which I work a lot, you have sort of hard particles as well as proteins that somehow can be think about as colloidal particles, some of them because they're compact globular polymers that are collapsed and that expose some attractive hydrophilic and hydrophobic patches on the outside. So once you restrict yourself to the colloidal system, then you have to go a bit to look what is, you can look what is the definition of such system, and you find that in fact is basically a dispersion. So you have a dispersion of a dispersed phase into a dispersed medium. So something like the green things is the dispersed medium, and you have this dispersed phase that is in this little medium. And what characterizes this system is the range of time, the length scale. So the length scale of this object is where you basically your subdivision of the two phases are 1 nanometer to 1 micrometer. So sometimes these are called also mesoscopic system because they're not microscopic in the sense of condensed matter. And from the way behaving of these two phases, you have all the different kind of rich behavior that we find in soft matter. Of course, we have, I told you about two phases dispersed into one another, and when I mean phases, I really mean thermodynamic phases. And so by crossing different thermodynamic phases, you get different colloidal system. So for example, if you have a liquid dispersed into a liquid, you can have an emulsion, something that is extremely useful in several contexts, particularly in food science. As well, if you think about having liquid particles that are now dispersed into a solid matrix, a solid medium, you have something like solid emulsion that are again extremely important for food science and several biology. So I will now restrict myself to one kind of colloidal system, that is the kind of system in which you have solid particles that are dispersed in a solvent, right? And so this is called a sol or a dispersion. Again, has a huge amount of application, and it goes from solid paint to soft paint to ink, but in some sense also a lot of, again, food science like milk and things like this. So I will focus on this particular of this kind of system here. So how do you treat this system? So we want to do statistical mechanics. We want to use the tools of statistical mechanics. And you do have in this system these macroscopic objects that are of the order of micrometer, hundreds of nanometers. So you are way above the length scale of the atomic and molecular system. So how do you treat this system? But very simply and put the way physicists do a lot of time is by coarse graining the degrees of freedom, which means that if you have those colloidal particles that sit in a solvent, like this little red ball represented the solvent, even if the solvent is actually much smaller than that. And generally, this system are extremely rich in the sense that you might have this, Sanat discussed a lot of these cases. You might have to coat them with a thin layer of polymers, so to stabilize them against van der Waals attraction. And whenever you have water or solvent, a lot of time you have that charges dissolve into your system, so you will have system of charges going around, and you might even have, as we will say in a second, polymer in solution that could interact with the overall system. So how do you deal with such a complicated system? So the way physicists do, which is basically reducing the difficulty of the problem, and basically we come out with effective interactions that are either, they can be derived, there are ways of deriving, they can be calculated by computer simulation, they can be only also think in sort of in an intuitive way, and there are ways of sort of coming out with models that basically allow you to map colloidal particles into atoms. So once you have done that, I'm telling you these are thermal particles because these are much smaller than the particle that Bulbul was discussing, where from micrometer down, I think you stop to be a thermal particle above 5 micrometer or even 10 micrometer. These are small, so forget about what we said about the granular system. These are particles that undergo thermal motion, so they follow Brownian motion, so they are ergodic, they explore space, you can apply statistical mechanics, okay? How and well is another thing, but they are thermal, and so entropy exists here, real entropy, in the sense that we have discussed so far, okay? So to give you an example, I think we have discussed this, and you will discuss, I think, a bit more next week, but a classical example of why those systems are extremely helpful and have been widely used in statistical mechanics as a test ground comes from an old problem of our spheres, and a problem that is intrinsically related to entropy. And the idea is the following. So you take an R-sphere system, I don't think I have to introduce it. It's basically the first step above the perfect gas, right? So now your particles are not anymore point particles, but they are spheres with a certain size. Well, it turns out, so you have just one control parameter, is a scale variable that gives you basically the amount of occupied volume by the particle. It's a dimensional variable. So it turns out that this system here was highly debated in the 50s because people, I think Kirkwood was the first one to say that he would expect such a system to have a phase transition. And this was a huge debate in the 50s because nobody was able to show if this was the case. So it happened, and again, you will probably hear a lot about this in Francesco's lectures next week, that Alder and Wainwright, and so Bernie Alder is one of the father of computer simulation around those years here that were really the time of booming of computer simulation. I think Monte Carlo is 1 or 2 years before, something like this, but the end of the 50s were the time where people started to have computers and people used computers to solve problems. And so they were the first to show that there was actually a first order phase transition between a liquid and a solid phase. Nowadays we know that this solid phase is an FCC, they knew, but now we really can measure the free energy of the system very well. And it's really a first order phase transition. And the reason why you get a phase transition has been explained to you before is that at a certain density, an FCC crystal has a larger entropy than equivalent liquids. And so the smooth stable phase becomes the solid. So now we sort of say this all the time, but at the time really we're really fighting hard. There were a lot of, there's a lot of history of conferences where people were really tearing each other apart on this problem. And so nowadays we know that basically the phase diagram of this guy is the following one. So you have a fluid, you have a crystal, and the two coexist at extremely precise density that are really known. And as a matter of fact, experimentalists use sometimes those density to calibrate their system. It's so precise, it's a phase transition, it's extremely reproducible and extremely precise, and so you know this. So what you see is that eventually, when you start to be too packed, you start to be in what is called the glass, but we will talk about this in a moment. First, let me say that all of this was back in the 50s, and then in the 80s, physical chemists started really to do a lot of advances, and they managed to, around the 80s, to be able to actually start to synthesize those particles I was telling you around, those colloidal particles, in extremely controlled way. Because one of the problems is that as soon as your system is slightly polybed dispersed, you don't have the crystallization anymore. And when you do that, you find this figure, which is, you find this result, which is basically you mix those particles at time equal 0, and then after 1 day, 4 days, you see that crystals start to nucleate. And the boundary of the nucleation is exactly the one predicted by the simulation. Really extremely precise. What you see is that when you go to high in density, so above 50%, you start to have something that after 4 days does not nucleate a crystal, or if you want, start to nucleate a crystal, but extremely slowly. So there's something whose life is extremely long here. And this is basically the glass phase we will have to discuss in a moment. So the idea of a glass transition is the following. So if you are able to study this system by simulation or by theory, there are different approaches to that. You could take a density-density correlation function. So when you discussed with Dasgupta, you discussed the liquid structure, you saw the static structure factor, which is basically the correlation of a density fluctuation at the same time. If we do this at 2 different times, we basically have a correlation between a certain density at a certain weight vector q, and at 2 different times. And we can average on this, and you can show that in a liquid this decays pretty rapidly as an exponential and is related to the diffusivity of the particle. So what happens is that when you start to be close to the glass transition, close to a glass, such a scheme here, which is pretty simple, starts to become very complicated, and you start to have this typical pattern of 2-step relaxation. And you start to develop the plateau, and in particular, you start to see a time scales that start to grow a lot. And what happens is that eventually, experimentally or in your simulation, this time becomes much longer than the time of the simulation or the experiments, and so the system is de facto arrested for what you can actually measure or see. So for us, this is this effect that is completely dynamic, is completely dictated by the dynamics of the system, is something that emerges in those systems before. And in fact, the system in this case is frozen. So if I go back to this, picture I showed you before, so now we know what we have here. We have a liquid, here we have an FCC, here we have a real quick system between the two. What happened here is that, in fact, approaching roughly 58%, the system starts to slow down. And the nice things about colloids is that they're big. They're big. They behave, I mean, if you do them well, they really behave as spheres as much as they can exactly reproduce the phase diagram as you would expect. So you forget about all the details, the charges that are there. If you're a good chemist, if you're a good colloidal person, you're able to really make real R spheres. And what you find is that then in this area here, you have something that you can see, because if you do experiments on and these are micrometer spheres, you can see them in a microscope, but as well, since they're bigger, the time scale will be much slower. So you can do a lot of experiments on them on time scales that are much slower than the time scale of an atomic and molecular system. And so this helps a lot. And so these are, for example, and then you also can use different probes because you can, I mean, you know, for nanoparticle, you have to use X-rays, but when you are on the micron, you have to use something with wavelengths of the order of the micron. So you can use light. And I think these are results from, I think this is light scattering. And you see that approaching, increasing the packing fraction, you do see this double relaxation that develop in the experiment. So these are actually experimental results, okay? Yes? I mean, it depends on the experiments. I mean,
how many bars of
3, 4, 5 decades from the microscopic decades, I would say. Yeah. Yeah. So simulation, we do get 3, 4 decades. Yes. Yeah. Yeah. There are a lot of, I mean, the problem is that in the experiments, there are a lot of things that kick in before, I mean, when I say you can treat them as spheres, you always talk about length scale and time scale with this certain time scale. So these things might start to crystallize, might start to sediment, might start to aggregate. You know, the sample will evaporate. So nothing that has to do with the physics of the system will go in the experiments, right? Yeah. Well, I mean, the problem is at equilibrium you can, but you can also do aging. People have done aging on the system, so you can access. The problem is, for example, for scattering, the problem is that to renormalize well your curve, you have to reestablish ergodicity at the end. And if the systems are not ergodic, you don't know how to calibrate them. So people have invented ways of doing this. These are the rotating chambers, these funny things that you saw. It is. But again, you fight not only with the timescales, but also with the really, I mean, the problem is that here you have to eliminate charges, match density, match contrast, and sometimes you have to obey so many things that the things behaves well for a very short time. And this is why I think like 90% of what you see in colloidal glasses is one system. You know, the PMMA and Dijkstra and It's produced from one guy. It's basically from one guy. So you'll see a guy is in every paper on colloids. Basically, a guy from Animal is Scofield. His art is to prepare the perfect sample, and he's every paper. So he puts all the groups in agreement for that. So that's the only one who doesn't fight with each other. So anyway, so just to give you a picture of why you get this double decay, this is really due to the intrinsic behavior of the particle in a dense regime. And so you have that the first decay is due to the fact that the particle will start to explore the local cage. It will be trapped, it will be extremely dense, it start to decorrelate by its position, you start to decay a bit. But then to get out of such a position, you need to have sort of collective motion that opens up channel for your particle to get out, and that's the second time you get, okay? So the microscopic is what is called, this is generally called the cage effect. I'm telling you here for our spheres, but the idea is always the same. You have these two characteristic timescales, that is the local exploration and getting out and restoring ergodicity, okay? So what I'm saying here is at equilibrium, so eventually you restore equilibrium, okay? So now this is the picture for our spheres, and now you want to add attraction, so I don't want to say much of attraction, but maybe I just want to put a picture. I think Francesco will really derive these results. It's a very nice result to derive, to show that if you take two particles, two R spheres, and you put them in a sea of polymers, and you add polymers to the system, those particles, well, I wanted to make a question, but it's written here. You know what they do? They will start to attract. And the reason for that is that when you put them next to each other, you gain a little bit of volume here. And this volume makes you gain space in phase space explored by the little particle. And so the entropy of such configuration will be larger than this configuration here. And this will turn into an effective interaction between the guys that bring them together. Something that was discussed for the first time by Osakura Osawa, and that derived this interaction that are in fact completely entropic, but that de facto create attraction between the particles. And what I want to say, yeah. So there is this is a really nice little statistical mechanics problem to play with. I think Francesco will do some some derivation on that. You have very different ways of doing. You can do it by entropy, by the free energy in the grand canonical, with osmotic pressure. There are like at least 4 or 5 different ways of deriving this result. So it's always nice to discuss it. And at the end, boil down to basically a gas of spheres into an exploded volume, okay? And so the important thing is that now you can control the attraction between these two guys, and in fact, the attraction between these two guys, the range of the attraction of these two guys, that will be another key quantity of whatever I'm saying now. It's regulated by the radius of gyration of this guy. So you exclude them depending on their size. The smaller they are, the smaller, the shorter will be the attraction. This is very important. This is very important because people have never looked at the statistical mechanics of object with short-range interaction before colloidal system. Why? Because there was no reason. You always have Lennard-Jones kind of interaction that, for me, working in short range are long range, but let's say are much longer than the diameter of the particle. But now, with this system here, you can really create a system with a very tiny and short attraction. And the change of that is dramatic. So already the phase diagram changes like hell. So this is the phase diagram of our spheres. This is the first diagram of any van der Waals kind of gas that you take from Lennard-Jones, you make your nice mean field solution. And then, in fact, you can show very easily that you can calculate with several different ways, but let's say in the perturbation theory, you can easily calculate the phase diagram of a short-range system. And what happens is that gas-liquid phase transition with associated critical point. Now I can have a critical point. I have attraction. So a critical point I can have. And this critical point goes down, it becomes metastable with respect to gas and the crystal. So this is just already the phase diagram is extremely exotic, okay? And in fact, this has huge importance because, for example, a lot of proteins behave in this way. They do have this metastable liquid-liquid phase separation, and there is all a story about how this speed up the nucleation of crystals, something that is incredibly important technological and scientific importance, okay? So already the phase diagram is changing a lot, okay? So you have this curve here that is liquid-liquid is there, but it's metastable with respect to the gas crystal. So the real phase diagram, the equilibrium phase diagram will be only between these phases. But still you have the critical fluctuation of this guy, okay? So now I want to discuss with you, so this is sort of all the results, but allow me again to see where I'm started in that, to tell you what we did in the last few months. And so now I will use the word phase diagram here in a completely wrong way, in the sense that what I call phase diagram now, it's the non-equilibrium phase diagram. So I will tell you where a system becomes basically a glass. So allow me to call it phase diagram. It's more a dynamical object. So it turned out that when you have, so if you remember what I did before, what I showed you before, is that if I do my R-sphere system, basically at 58, roughly, I start to have this glass here, right? Now the question is, I take this short-range particle, and I start to put attraction between them, and an attraction that is short-range. What I mean short-range, I mean extremely short-range. The range of the attraction is percentage of the diameter, so something extremely unusual. So what happens is that if I add now I have an attraction, I have to add something that gives me the idea of the energy of the interaction. So if basically here I have something that is like 1 over T, so the temperature goes down in this direction, this line here does something funky. So basically does something like this. So you basically end up having a glass all around here, but between the two glasses you have a liquid. So you start to have a liquid that is in a pocket between two glasses. So that means that if I move like this, I basically can start from a glass, which is pure R sphere, because here at T, 1 over T equals 0, I start from R spheres. I go away and I melted the glass and becomes a liquid again, and then it reclassifies. So this was very unusual. This was predicted by several theories, in particular by Brightmouth coupling theory. And this is what I want to tell you a bit about. So in this area here, you have a colloidal glass, as I said, is what I will discuss a bit more in details in a second. And let me say briefly something about the low density. So when you go to the low density, you know that you have this phase separation. This is the gas-liquid phase separation that you have from any attractive gas system when you get an attraction. So what the people notice in this system, so this depletion-driven colloids, is that at low density here, if you do the experiments, a lot of time, you would find a gel. So an arrested space, an arrested matter that was somehow composed biramified structure. So the density here is so low that you have to form something that spans space, and you do form something that spans space, and it is arrested and it's capable of sustained stress. So here we have what is called a colloidal gel. So everything I'll do and show you, it's before I turn into the new results, is for a very simplified system, which is just a simple square well. So I really gave you the minimal model on top of the square well of the R-sphere to have an attraction. And so this is generally, we did this for one component, two components, several particles, different dynamics, but I really want to give you the story. But what I want to say here is just that this is result of mostly of simulations. Okay, so let me say you something about just one slide of what happened here, because I think it's interesting, is that, so first was solved basically this problem here, and then people remain a bit puzzled about what was going on here. And then what was clear is that in colloids, basically what you do is that if you quench your system down here, you start to, in principle, your thermodynamics tells you that you would like to have a gas and a liquid. As a matter of fact, you stop before that because your system starts to coarsen, but eventually becomes so slow that it doesn't move anymore. And in coarsening, you form this ramified structure that are the gel, okay? And so this has been seen in proteins, has been seen in colloids. So just to tell you about something. So you see again, something that was observed in simulation and theory was then confirmed by experiment. So this is typically of this field. It's very easy in a sense. I mean, easy to make experiment to confirm what you see, okay? So I want to go back to the glass, okay, now. So what I told you is that if I move along this line here, I pass from a glass to a liquid and then a gas again, right? When I should have probably put scale here. This is very dense. This phenomenology here, you see it above 58% in packing fraction. So the system is extremely dense. Even if you would like, if you could in principle create this homogeneity because you have attraction, the system is homogeneous per se because it's all occupied this. And so what you find is that if you move along this constant density path, you make your simulation, you study your diffusivity, so you can study diffusivity, you can study the relaxation time of your correlation function. Basically, what you find is that in temperature, so going down here, you pass from something that is low, so the diffusivity goes up, the system speeds up, and then goes down again. So you have a maximum in diffusivity that is the basis of the origin of these re-entrants here, right? So these are the result of simulation, and you see that by increasing the density, you get more and more extreme. And then you can, to rebuild these curves here, you can make a little game and trace on the phase diagram eco-diffusivity line. So line at which the diffusivity is the same. And then you actually map out exactly this re-entrance here that is seen in the simulation. Yes? And you think the gel is on this side? It's very, very down. So you need to... It doesn't ever encroach on it. So, I mean, it's a matter of... I mean, you go eventually into... I mean, what drives this glass here is exactly what drives here. The difference, so bonding. Mm-hmm. But the difference is that here, you don't have enough space to generate these homogeneities, which you do have here. So sort of from here to here, you continuously go from a dense phase of sticked particle to a dishomogeneous phase of sticked particle, which become a network. And then eventually you go in all the LCA and all the classical fractal gels. It's a very good question. So, so if you look at the structure factor, it changes a bit, but not that much. I mean, generally, well, you do see that there is more localization of the particles, but the structure itself is not dramatically different. Okay, it's a first order answer. It's more complicated than that. Let's say the most of the things you see them from something that pertains to dynamics. So it depends what you call structure. So then you need to look structures, but in a dynamical sense. So what you do is that start to see, for example, dishomogeneity in the dynamical sense in the system. And then you start to have a string of particles that moves around, and this can change between these two. Okay? So you'll find, for example, that the kind of activated process that you have here and here are different. But to make an activated process, so in other words, I give you two pictures of the two guys, you will have bad time to say the differences. If I give you a picture times 0, I mean a series of pictures, and then you say something. First order response. Okay, so a lot of these things come from the analysis. Yes. Yes, yes, yes. So it takes, so it's enough here, because basically what enters in in mode coupling theory is mainly the information around the peak of the structure factor, which is basically the caging. And the caging in this guy changes, and the little change you have in the structure factor are enough to generate those reentrants here. I mean, in fact, this was first observed by mode coupling, then confirmed by simulation. So this is a pure prediction first. So we have to deal. I mean, really depends. So the first works that were made on that were made on the Baxter model. So the Baxter model is infinitely thin, and so the effect of that is that you have this Q vector that continue to oscillate and make a mess the equation of mode coupling. And so you see that the more modes you add, the more the density mode changes. In the moment you start to have a finite, so basically when you have these square wells here, you have, at the end of the day, you have two length scale. 1 and 2, right? Then the tail of your structure factor behaves better, and there's no problem in Yeah. And a lot of other prediction. I mean, I will not enter about, but a lot of the prediction of mode coupling, there is a lot of to be said about the shape of the dynamic structure factor is predicted by that. There is a logarithmic decay. There is an endpoint. I mean, I could speak 2 hours about this. I don't want to bug you about this, but let me say, I mean, credit to the theory, we know the bad things about MCT, but one of the good things is that it does predict things. And this was the case. I mean, okay. So what I want to say is that, after all of this was first predicted by theory, by mode coupling theory, you probably will get a bit of mode coupling theory next week. This was then confirmed by computer simulation, and I'm just citing, different system have produced this by computer simulation, and also that was confirmed by experiments. So here is this colloids plus polymer, and what you see is that, okay, this is the content of polymer, which means that basically the R sphere is here, and so it's really like this guy here. So 0, you have R spheres, no polymer, and here you increase the attraction. What you see is that your correlation function are up here, then they decay down here when you are in the middle of the liquid, and then you shoot up again. So this is exactly what is predicted by the theory, and this reentrance was pinned down in the 2000s. Okay. So now, what is the end waving? I like to sort of think of what is the end waving reason to see something. And so let's think about it. You have R sphere. They're glassy. On top of glassiness, they're already slow. You put attraction. Attraction would tell you that something slows down the things. But this is not happening. Actually, speed up the thing first, and then not. So why is that? Do you have any idea of that? I don't want to get too much into this, so you know, I have an idea of that. So the reason is, the waving reason of that we had at the time was that, so in an R sphere glass, you sort of particle, it's sort of simplified version to single particle. Here you have to think that everything moves around. But let's focus on a particle. So a particle will stick and will be localized by basically a cage of the neighbors. So now you start to have some attraction, and what happened? Well, the particle will start to stick one to another. So they will start to form some bonds, and these bonds will localize the particle in such a way that channels to get out the particle will be created. And when you do that, the system first speeds up, but then those bonds become so dominating that the system stops down again. So the first effect of the attraction is to create those channels. And now, why short range? Why does it happen for Lennard-Jones particle? Why do I have to have basically when I told you about this length of this is the range of my attraction. This has to be roughly 0.03 up to, let's say, 0.10 of the diameter of the particle. So extremely short. After that, you don't get this reentrance anymore. Why? Huh? It's not really that, but really the system is so dense. Then imagine that you get this particle, right? I had a picture, but I forgot to put it. And now you start to grow a shell of attraction. There will be a moment in which the shell will form bonds and will start to make particles stick together. If this this range of this potential becomes too much, all the particle will start to just lower the energy. And so there will not be any, they become back to be basically repulsive dominated, just with a lower energy. They will live in a sea or low energy, and there will be no difference. And this is why this effect here, if you grow the range of the potential, it actually disappears. Okay, and you can do this, you can prove it. Mode coupling theory predicted, simulation predicted, and so on. Okay, so I have finished the part of what it was. So this is, actually this is no story. I haven't worked on this problem for almost, more than 10 years, I would say. Yes? Well, I know that there's not it's not an optimal, I have an upper bound. So basically we showed that as soon as you are below something like 0.1 of the diameter, you start to have, basically what happens is like, let's say I'm decreasing the range, you pass from this, then you start to do this, then you start to do this, and then you start to do this, okay? So the shorter the range, the more reentrant the thing is. So there's not a way of optimizing. The shorter you can make it, the more it will be your liquid pocket. And then there is a lot of funny things that happen here, but again, I don't want to get into the details. Okay? Now, so I haven't worked on this problem for a long time, and then last year we started to relook at this problem from another point of view. And the idea is that everything I told you so far is for isotropic particle. And we wanted to see what was the effect of introducing directionality in this picture. So what we did is that we took a model that is the direct generalization of the square well with directionality. So now I need to understand what the model is. Once you have understood the model, you can really follow me well. And the idea is the following. You have, in fact, your interaction potential is between two particles, and you have R-sphere. So the particle, no matter what the orientation is, they will always bump into each other as R-sphere. But now the square well part, which is just the attractive part, is modulated by a function that depends on the orientation of the particle. So my little particle now will have little patches, little highs of certain openings. So I can modulate the opening of my patches. And the idea is that this model that was introduced by KERN-FRENKEL, this function here, if the two patches are crossing at an angle that both patches cross, basically are facing each other, they are not facing each other, the F is equal to 0, and so they behave as R-sphere. If the patches are seeing each other, is equal to 1, and then they are attractive. So what the simply shows, it's harder to put it in form. What I'm saying is that my particle now have a sort of attractive patch here, right? And two particles will fill this square well only if the two patches are seeing. If they come with the wrong angle, they will not see. And so now you have a different variable in the system. You have the opening of your patches, as well as how many patches, and as well as how you put them on top of them, okay? So for us, there is this theta will be the opening of your patches, and n will be the number of patches we will put on the particle, okay? And so what we did is that we investigate the same problem, we look for the same problem, but now for those patchy particles, right? And the first question that drove our curiosity was that a lot of people have done a lot of studies on those patchy particles at low density, and we asked ourselves what happened at high density. And so it's clear that at high density, the main things that you find is this maximum in diffusivity, right? And so we ask ourselves, would you get the same maximum in diffusivity if you had patchy particle, right? So what we did is that we stick to a density, so 58, and we moved exactly at the same temperatures. So the advantage here is that these are exactly the same model. One is square well, so this is square well. The other is square well that works only when the particles are oriented as you would like. So you can really compare them pretty directly, right? And so what we did is that then the problem is that, of course, you have now a zoo of particles, because how do you put the patches and so on? So we have to choose some of them. So the first things we did is that we look at these reentrants, and as a matter of, you do find, so this is as a function of the opening, so this is, say, 6 patches. They are arranged as indicated here, and you change the angle of the patches, and what you find is that when the angle is big enough, So those patches are made in such a way that you can only form a bond for each patch. When the patches are large enough, you basically recover the square well. Sorry, what I wanted to say is that when the patches become so large they cover completely the surface of the particle, you recover the square well. So we don't have overlap of the patches, basically. And so what you see is that by reducing the angle of the patches, a bit of the reentrance goes away, but it is indeed there. And then eventually when the patch becomes too narrow, they disappear, you basically become an R-sphere because your patch is so small that it will be very unlikely to hit it. And so it will be many R-sphere. Or you start to hit it by very low temperature where doing simulation with BMS. And so you find this for 6 patches and 12 patches. So the first message that we got was that in fact we do find the maximum in diffusivity and the reentrance in this directional patch. Now, the next question we ask ourselves is, let's say you want to create particles, right? And you are capable of doing the geometry you want as much as you want. So what would be the optimal way of doing them? How you would optimize them to make, for example, a glass? So now what we do is that we focus just on one temperature, let's say 0.4, where systems are glassy enough. And what I'm saying is that let's focus on a percentage of coverage. So this quantity key here is 100%, is the particle is completely covered. So 100% you have a completely covered particle. And when you reduce it, the surface cover of your particle goes down, right? And n is the number of patches. So basically what I'm saying is that I want to test those particles here. They have the same amount of coverage of particle. So the question is it better to have 3 big patches or 20 small patches? Let's say I have the same amount of material I can put on top of this particle. What would be better? Anybody has a guess for that? Largest particle. Somebody else? What's the best way of doing? She knows because she did the work, so she cannot respond. Okay, we were surprised as well, and I give you the result. So what we do, let's just focus. We did diffusivity and all of this, but let's just take the correlation function, right? So this is the correlation function for 3 patches. So same temperature, same amount of material on the surface, which amount, by the way, to the same virial coefficient. So roughly, for patch value, this is really the attraction need that in average they feel is this. So 3 is there, 4 is there, 5, 6 is there, 8 is there, boom. This is 12. So 12 jumps completely out. The icosahedral structure, when the particle have an icosahedral structure, you get something that is horribly slow with respect to the other. And then you go to the square well, to the 20, go back, and then square well is the same. So the 12 is the one that jumps out of the pack. So why is that? Well, we're extremely puzzled and pleased with these results. And at the first we thought it was bogus, was something that was not working. But Susanna did all the trick and the calculation and the check we asked her. And now we are pretty convinced that this is a robust result. So everything we see, I can show you also for the Q vector. So, this is a correlation function for one Q vector, but you can do for all of them because you could say, oh, well, maybe you landed on a bad Q vector. But as a matter of fact, you see all the patchy particles are here, and then the 20 jumps here at the same level of the R spheres. And in fact, if you reduce a bit the temperature, it goes even farther. So it really, yes, 58. And it's a binary mixture, 1.2 size ratio. Yes, yeah. That's what we find. That it becomes something else. We haven't looked at that systematically. So we aimed for the one that was dense, really to see this effect. And we found it was a posteriori, everything is not a surprise. But at the moment, we were surprised. You didn't respond, by the way. You didn't say that it was 12, the one you expected, though. A posteriori, everybody. Well, we were surprised. Yeah. And also, one thing that is surprising and they were thinking about is that, of course, you have a way of suppress crystallization here, right? You need also a way, eventually we hit on a way of suppressing crystallization that does not suppress local icosahedral order. Because, you know, that's not given because one of, you know, depending on size ratio, polydispersed, and it turns out, well, I'll come back to this, but it turns out that this size ratio is the same size ratio of some of those lava phases that have icosahedral, you know, some of these front half. So, sorry? Yes, yes, yes. Yes.
So that is very similar to this. Like you have very large anisotropic.
Yep. Yep.
But both cases find that like the point structure depends a lot on how many heads you have.
How many? How many?
Like how many? Let's say like let's say there are 3 bonds which connect together. In that case, the structure is like a very large extent by what is the orientation. Why don't something like that? Just you would imagine that. This should be similar to what you do.
But I've lost what you see. I don't understand that. What you mean by so what you see? You say 3 bonds.
So in that case, like probably they would crystallize where the bonds are like aligned.
Yeah, yeah.
But here it seems to be that you always have to
Yeah, I'll come to this in a second. So, so if I count the number of bonds in my system, I do see that with respect to the square well, the number of bonds goes up quite radically when I reduce the temperature. And so I see that, in fact, the 12 is the one that has the largest explosion of bonding. And in fact, these 3 curves that seems very similar, you can just say, I mean, if you take the temperature at which those 3 cases reach 3 bonds, and you rescale by this temperature, they all collapse on the same curve. Because basically what's happening is that here you have particles that are rotating, so differently from the square well, which has no rotational degree of freedom, here you have rotational degrees of freedom, and by stopping them, you lose entropy. And so you stop 1, you stop 2, you stop 3, but by the time you stop 3, you have stopped all the rotation, and then this explodes. Yes? Yeah. Yeah, we go look for 40 and 20, and it's the same. I'm showing just 40. 20 and 40, that's all we checked, right? Yeah, and that was, okay? Yeah, I'm coming to this. Is what we, then is the next look. We look at this rotational invariant, so you can characterize the characteristic shape of a cage of each particle. And the idea is that you have the structure here, and without entering into the details, you can define some observable that are called rotational invariants that gives you some idea fingerprint for each particle of what is the local structure. And so it's like hunting for different structure will have different fingerprint, and then you can basically tag each particle with something that is specific of the structure. And so, for example, and generally what you do is to look at 2 of these rather than 1 is a better way to look at. So what we focus our attention was Q6 and W6. So these are numbers that if you are in a specific icosahedral cage, you are driven, you are those numbers. So the idea is the following then. So now I plotted these 2 quantities, W6 and Q6. And I will put a point for each particle. So if a particle is in a perfect icosahedral point, it will be here. If it needs an HCP point, it will be here. If it will be in FCC local structure, will be here. And so then basically what you see is that at the beginning, the spectra is pretty disordered. And then when you start to reduce the temperature, the particles start to crystallize, to clusterize around the icosahedral, which makes sense, right? Because it's particles are pulling toward the structure there. And in fact, you can measure the icosahedrality. You can sort of make a criterion and count the point, a different way of doing. We did the stupid way, which is counting point, but it seems to work pretty well, and we tested all other. And this allowed us to tell us what is the number of particles that are in an icosahedral environment. And when you do that, you can compare with the other structure, and what you see is that by reducing the temperature, the actual number of icosahedra goes down. The square well, which will be eventually slower, grows up a bit. So eventually this will become slower than that, and we know this by the simulation, but the icosahedral wall will actually explode really out of reach. So basically what you have found here is that you have found a recipe for make a glass that is extremely slow, extremely efficient in relatively dynamic. And the way you do this is by optimizing structure, by choosing 12 neighbors. And so to finish is why should I care? So there are two answers to that. The first answer is that in fact, as in the 80s, there was a lot of emphasis on creating those particles that allowed us to make square wells and attractive and nice sphere and so on. Nowadays, people are capable of making a lot of these directional particles. Here, for example, this is a Kagome lattice that is formed by directional interaction of colloids. So these are colloids deposited on a surface. You can even functionalize them. And in a sense, protein itself, they are patchy particles for the very same reason. Now, of course, that's sort of way far away to be able to do the system we are going to propose. But you know, the work is going on in this field from the experimental point of view. We are the first to look at this. And the second reason for that is a bit more, let's say, fundamental, and it goes a bit to what Sri was saying. And the idea is that this, so this is a nice review by Paddy and Williams, Paddy Royal and Williams, in which there is this idea of the Frank conjecture, and the idea is that basically, if you take just isolated particle, the ground state for Lennard-Jones particle, for example, is an icosahedra, if you take a particle. So in principle, you would like to fold in an icosahedra structure, but then you cannot pack the space with icosahedra because they are not able to do that. And so in this frustration of these two effects, you have the glasses that emerge. And in fact, these icosahedral structures are seen normally in simulation. So again, this is just symmetric isotropic potential. They show when you reach the glass transition that you have an explosion of this icosahedral structure. These are simulation. You see them in metallic glasses, so these are experiments, and you see that they grow up again, and you see even in gels, so in colloidal system. So what you're saying here is that you know that those icosahedral emerges due to this frustration of space in glasses. And basically what you have done, we have worked on the contrary. We have made something that really wants to locally form that, and we show that we can go the other direction. Then basically will be the slowest possible case, okay? So with this, I finish. I just thank the people who have done this job. So mainly is the work of Susanna here, who has a poster where she discussed also the rotational properties of these things, and Frank Smallenberg, who arrived last year to join the lab, and Rick, who's been in the lab for a few years, and for what was the first part, there are a lot of people I have to thank, so I mainly go to the one with whom I worked with. There were the people in Rome with whom I did a lot of work, and I did my PhD and a lot of work. So just put the main with whom I did the first part. But there are many more.
So maybe we take questions after he.
Sure.